Welcome to the NMSE Verma Laboratory at the Department of Chemistry, Indian Institute of Technology, Delhi. Our research focuses on the rational design and development of nanostructured materials for sustainable energy conversion and environmental remediation. In this video, we present one of our recent studies, in which we investigate how engineering the morphology and heterointerface of tungsten oxide and titanium dioxide heterostructures enhances photocatalytic hydrogen generation from ammonia borane. Developing efficient photocatalysts for sustainable hydrogen production remains an important challenge in clean energy research. Ammonia borane is an attractive hydrogen storage material because of its high hydrogen content and safe handling characteristics. However, its practical application depends on catalysts that can efficiently harvest light and promote charge separation. Tungsten oxide and titanium dioxide possess complementary electronic properties, making their heterostructures promising candidates for photocatalytic hydrogen generation. While previous studies have primarily focused on either morphology engineering or heterojunction formation, the relationship between synthesis strategy, interface quality, and photocatalytic activity has not been systematically investigated. In this work, we address this gap by comparing in situ and ex situ synthesized heterostructures of tungsten oxide and titanium dioxide, demonstrating how simultaneous morphology and interface engineering leads to enhanced hydrogen evolution. To investigate the influence of synthesis strategy on photocatalytic performance, we first synthesized well-defined hexagonal tungsten oxide through a hydrothermal process. Optimizing the morphology of tungsten oxide provides a suitable platform for constructing efficient heterostructures. We then fabricated tungsten oxide and titanium dioxide heterostructures using two different approaches: in situ synthesis, where titanium dioxide is grown directly on the tungsten oxide surface, and ex situ synthesis, where the two components are prepared separately and subsequently combined. By systematically comparing these two strategies, we examine how the synthesis route influences morphology, heterointerface formation, charge transfer, and ultimately photocatalytic hydrogen generation. After synthesizing the heterostructures, various characterization techniques were used to establish the structure-property-activity relationship. The materials were evaluated for hydrogen evolution through ammonia borane hydrolysis. Bare titanium dioxide and tungsten oxide show low activity, but the formation of a heterostructure enhances activity. Overall, the results demonstrate a strong light-induced enhancement in catalytic activity. In summary, we successfully synthesized tungsten oxide, titanium dioxide heterostructures using both in situ and ex situ approaches, and systematically investigated the influence of the synthesis strategy on photocatalytic hydrogen generation. The in situ heterostructure formed a stronger heterointerface, enabling more efficient charge separation and faster charge transfer, which resulted in superior hydrogen evolution compared with the ex situ counterpart. Furthermore, the catalyst exhibited excellent structural stability and recyclability, highlighting its potential for repeated use. Overall, this study demonstrates that interface engineering through an in situ synthesis strategy is an effective approach for designing efficient and durable photocatalysts for sustainable hydrogen production. We sincerely acknowledge the NMSE Verma Laboratory, the Department of Chemistry, IIT Delhi, and our funding agencies, including CSIR, the Royal Society of Chemistry, and the UGC, for their continuous support. We also thank our research group and collaborators for their valuable contributions. Thank you for your attention.